It's a little bit about the status and why certain things are important, and maybe why certain things are important that we necessarily don't think it is important, and why we're facing problem and how we can fix it and how we maybe cannot fix it. Okay. So we're talking about kind of approximate inference for latent Gaussian models. It's essentially what Helen was talking about a little bit, especially in the first example, if she was doing it the Bayesian way. It's pretty fast and accurate, has a very nice interface. We can do a lot of various models because we have a lot of a quite unique set of non-standard features that allow us to do kind of crazy things and useful things within this scope of latent Gaussian models. And it has also become kind of quite popular. So the aim of this talk is essentially to discuss a little bit why marker models, and this is in the Gaussian context, like Gaussian marker and fields, are so important, and what we sometimes can do if we have models that are still Gaussian but don't have this kind of marker properties. And essentially also kind of computation limitation due to size. Size is a little bit, size is not just n, it could be another m, but it also depends on other things, okay? So size is a little bit kind of undefined. So we have a size problem if the size of the model is a problem, okay? So I want to discuss certain strategies to go beyond what's possible today, you know? Still using the same kind of deterministic approach and still trying to solve the problem in general. So what is this latent Gaussian models? It's a very, very simple construct. You have hyperparameter, essentially parameters that are non-Gaussian. You might think of it that way. We don't have too many of those. Then we have something Gaussian, and here I write precision matrix. You have some mean. So you have we want this to be Gaussian, so this is like Gauss marker random field, depending on these parameters. And then you have conditional independent observations. This is like the simplest setup. And what really we want to do is kind of approximate marginals for the hyperparameters, but also for the latent field. Okay. The point is that this kind of setup that we have here is very, very simple. Okay. You have some hyperparameters. They are my dimension 2, 3, 4, 5 normally. You have some Gaussians, you have some observations, and that's it. So it's a kind of quite boring kind of setup because there is no kind of exciting things here, except that it's it covers a lot of the most common used models. We have all these GL, generalized linear mixed, and all these kind of additive models, smoothing, functional data, all these kind of funny things. They can all be kind of mapped back to this framework, okay? So this framework is very good for a computational kind of, you do your modeling, you can map your model back to this framework, you can solve the problem, you can give the results back. So this doesn't say anything how you should do the modeling. If you have a model that fits into this framework, then we can do the inference very quickly. Okay. Here is, I'm going to show you two main examples, mainly to kind of pay tribute to the two main people who have done amazing lot of work to make this work. One is this Nature article 215 about this is the effect of malaria on the kind of essentially on the basis on the behalf of the World Health Organization. And this got quite a bit of kind of press release. There was also interview by the top World Health Organization people discussing these things. There is another one by Gavin Shaddick from Bath, have done amazing work on doing this air pollution analysis. This is like a global data. This is again from the World Health Organization. These are a large-scale model that is done by this software, and also got news in India, or even Delhi is not a good place to be. Okay, so So that's a kind of certain, that's kind of the setting. I want to discuss a little bit the importance of being Markov, what Markov properties really give, and what you essentially can do if we don't have it, or sometimes do. So how this kind of model is defined is that we're essentially doing it within the kind of linear, like within the additive model context. So we're essentially having kind of fixed effects, and we're adding kind of terms. And the interesting term is what we call the F. The F is some kind of Gaussian model. It could be a time series model, it could be a model for a spline, it could be a random effect model, it could be a measurement error model, something Gaussian. Okay? The important that this kind of model is essentially Markov, otherwise things will kind of break, or it will kind of go bad as the kind of dimension will increase. Okay? So kind of being Markov is essentially for the computation to scale well. And one of the things that is kind of essential is that if all the models, all the prior distributions here are Gaussian, we need to kind of construct a joint distribution. The point is that to construct a joint distribution, if every term is Markov, is trivial. Okay? So if you have this kind of hierarchical setup, X is some normal with some precision matrix Q, and you have data where X goes in the mean, it's just a simple example, then the joint precision matrix is kind of trivial. Okay? So it's just plug and play. If you have 3 terms, you just extend the matrix, you just plug in these things. There is no matrix products, there is no inverse, there is nothing. Okay? Which means that we can easily construct this joint model, and we can easily evaluate it when all the parameters change. Okay? So if the hyperparameter change and we have to do a lot of work, we have to redo it every time. Okay? Here is trivial. Okay? And this is a tiny detail is so important to kind of don't see, because it's just there, and without this nothing would kind of really work. Which means that to construct joint models for all these parameters, the linear predictor, the fixed effect, all these kind of F terms, is kind of trivial. And we can update this joint model as we have parameters. Okay? The other thing of being Markov is that you can really factorize, you can do all this kind of numeric linear algebra very quickly. You can factorize precision matrix, less decomposition, you can solve it. You have the determinant, or the gradient of this is essentially what we need. You can also invert, you can take the diagonal of the inverse, or find the inverse of also the neighbors, and this kind of thing. The point is that it only depends on the graph. So these are numerical algorithms that depends on the structure. It doesn't depend on the numerical values in the matrices. Okay? Which means that they are kind of general, and whatever numerical values we plug in, we take the same time. Okay. So essentially, what can we do if we don't have Markov? So sometimes we're able to kind of reformulate the problem to obtain Markov. So let's say you have this differential equation with random right-hand side, second derivative. If you augment this, you have it augmented on the is Markov on the augmented space. Is the derivative missing? Could be. Sometimes you can kind of do this, you know. The other thing is that we can kind of approximate things. If it's not Markov, we can find a kind of Markov model that is close enough. Okay. One of the such things is Gaussian fields. Like if you're going to spatial statistics, you have covariance functions and such things. A class of models that is kind of popular is Matern covariance functions. Okay, we can look at them in the continuum as a solution of a stochastic partial differential equation. Okay, this is what's said here is a constant minus the Laplacian. raised to some power, and you have the Gaussian field, and you have kind of white noise on the other side. Okay. This is Markov in a continuous sense, but if you kind of discretize it, it's kind of not Markov anymore. But it turns out that at a kind of numerical solution, if you can base it on finite element methods, if you write the solution as a linear combination of basis function, and these basis functions are kind of local, then it turns out that the distribution for the weights are kind of Markov. Okay? Which means that we can take areas, we can make triangulations, we can kind of build models, think in continuous space, and kind of build models that are Markov. And it's like the weights that are Markov, but still the kind of we have a continuous representation of this model. We can also go to sphere, then we obtain kind of matrices like this. It's very quick to compute. We can also change the geometry. So we can define this kind of PDE to also depend on the geometry. So we have dependence going around islands. Okay, so here is this is outside Finland. So we have the dependency going around all these islands, kind of obeying this kind of geometry. And this is also very easy to do. Again, the solution is again Markov, and the time to do this is the same as to doing kind of regular things. These are some kind of new results. This is about fraction Gaussian noise. These are long memory processes in time series. Kind of popular in kind of climate science, where the correlation function has kind of this form for the Hurst. The h is called a Hurst exponent. The point is that the decay is much slower than kind of normally. You don't have exponential decay, but you have this kind of polynomial decay like this for large k. Okay. The point is that if we only look at kind of realization of this process, you get matrices that are kind of tuplets, and then there exist kind of exact algorithms for this, which cost n square. But as soon as you do conditioning, if you have, this is a latent model, you condition on data, all the kind of the tuplet structure is easily lost. Also, if you use this in connection with something else, all this kind of properties is just lost. And then you quickly go into n cube. Okay. It turns out, and this is kind of, it turns out that we can kind of approximate this kind of model with something that is Markov. Okay. So we can take a finite mixture of autoregressive processes with some weights and use that to approximate the fraction Gaussian noise. And it turns out that in this case we can obtain linear complexity, okay, even when we do conditioning, because we are back to the Markov kind of world where the numerical values itself doesn't matter. Turns out we only need 4 elements in this kind of mixture, and this is already also implemented. Yeah. So here, just to show this kind of what you can obtain, is that this is a correlation function from the fraction Gaussian noise. And if I do this mixture, this is what I get. I just show you some of the dots here. It's almost perfect. Huh? This is pretty good. Yeah. So what's happening here, because we want to maintain this Markov property, as soon as if you take this sum and you marginally out, you integrate out autoregressive processes, the Markov properties disappear. So the cost of doing this approximation is that we have to carry with us all the kind of the autoregressive processes in the approximation and the sum, the weighted sum. So this is what you see here. The kind of I'm not that tall. Yeah, you see the 3 blocks. These are 3 autoregressive processes, and then we're forming the sum. Okay, so this is the joint model. So we have a model on the larger space that is Markov, And if you do the reordering, you get a constant bandwidth, so the cost of doing this is kind of linear. And these are kind of coefficients you can get out for this kind of approximation. So this is like a gigantic kind of computation, takes like maybe 10 hours. You just compute all the coefficients, you do the interpolation in some other space, and you tabulate everything, and you just do a kind of table lookup for dealing with this. Of course, we run into computation problems with our kind of software, and especially this is related to essentially problems with space and time. Okay, so think like three-dimensional problems, and the main issue is that the dimension easily get large. If you think space and time, you have 100 by 100, which is not too big, and then you have 100 time points. Okay, and then we easily up to 1 million. Okay. The other effect that hits in as soon as you have problems in space and time, the matrices is a little bit more dense. Okay, you're not only neighbors in space, but you're also neighbors in time. So there are essentially more neighbors to account for, and so therefore, for that reason, the kind of numerical algorithms will also run slower. So essentially, the cost is like n squared in 3D, and if you 2D is like n 3/2. So we have to pay square root of n more, but also n is higher, and the memory increase. Okay. So essentially, what can we do from this point on? Okay. So if we're still thinking of going in the path where we kind of compute everything with kind of direct solvers, direct linear algebra, essentially the situation is now is that we have a parallel loop over, and we are factorizing matrices within the loop, which means that the factorization is serial, but we have a parallel. It's doing things in parallel on a step higher, level higher. If you have really huge matrices, maybe we have to require still a parallel loop, but we also have to be parallelized, factorized Q. Okay, so we have to factorize matrices also in parallel, because simply it's kind of, you cannot do it on one CPU anymore. Okay. Then we easily into computational clusters. We have this MPI method, what's called yeah. An issue here is that there isn't that many kind of sparse matrix libraries exist for doing this. There is one based on France from Fairfax called MUMPS. There is another one from Lawrence Berkeley National Laboratory, and they are kind of, the license for those are kind of okay, so it's kind of possible. There are licenses for others, like there is a very good one from IBM Research, but the license would not, the license is a problem. Okay, so there isn't that much to play around with, but these two are kind of can do well. So this is one kind of direction we can go, and the other one is to look at other kind of approximation techniques. And of course, we're not the first one to look at this, and especially there is something called hierarchical or H matrices. It's like a numerical approximation technique for huge matrices, dense or sparse. The point is that they are motivated from the same problem. Okay, so they are motivated from large matrices constructed from finite element methods, which is essentially the same thing we're doing for kind of constructing models in space and time. Okay. These techniques scale well, and there are numerical libraries that support parallel computing and MPI and so on. Has good theoretical justification, and this is something that we kind of work, this is the direction we kind of working on now. Essentially, the idea is that you have a matrix, you kind of recursively divide it into 4 blocks, and you divide these again. And then you do the kind of analysis of this to see how heuristic, how well, or what is the rank I need to kind of approximate. How little rank can I kind of get away with. So all the red blocks are kind of full rank matrices, and all the kind of the green ones are essentially no more than rank 4. Okay? So you're doing kind of low rank approximations of these kind of small blocks, and all the matrices kind of analyzed to map this into a kind of a block matrix of lower ranks. Okay? And then you can do exact computations on these kind of block low rank matrices. Okay? Another kind of strategy that also been around is to use iterative solvers, and essentially solving large linear systems. Okay? Qx is B. It's really nice if you look at it. This seems like this is the solution to everything, because you don't need hardly anything at all. You're only doing kind of matrix vector products. Okay? And it's a little bit that the kind of our way of thinking kind of hit back on us, because many of the matrices that we are interested in converge very slowly in this framework, mainly because we like to do things in, like, I have a spline, I want to construct a spline, I have 100 different knots, so I have 100 dimensions, but the effective spline is very smooth, so it lives in this kind of 5-dimensional subspace, which means that there is 95 dimension that is essentially shouldn't be there. Okay? So it's kind of, you have a lot of kind of built-in singularities almost, which kind of slows things down. And also it's kind of less obvious how to get quantities like the log determinants or the derivative, which you need to kind of estimate this kind of hyperparameters. So it looks very nice, but there is a lot of problems also here. Variational methods, there have also been some new developments in that area that might be useful. And why I put it up here is simply because essentially we know what the solution would look like. Okay? So a good enough approximation for a large model is say that the hyperparameters are normal with some precision matrix that we could even take as a diagonal matrix. Okay? These are transformed hyperparameters, log variance and so on, so they are approximate normal. If we know the hyperparameters, then we know that the latent field is kind of Gaussian, and we essentially know what the kind of the precision matrix should be. It's like Q of theta plus something on the diagonal. Okay? Q comes from the prior, so this is our full control. We know approximately what the diagonal should be, and also what the kind of linear offset should be, because they come from the first and second derivative of the log likelihood. Okay? So we have a lot of control, we have a lot of information what the solution would look like. And then this could be indeed become possible. But it's still unclear if this will scale well enough. You know. So essentially, the latent Gaussian model is a very important model class. Although it seems very boring, it's one of the most important ones. And Gauss Markov random fields, being kind of Markov, simply allow the Bayesian inference to really scale. It scales really nice up to some points. For normal users, this is fine. You can easily deal by models of 100,000, it's fine. But if you're coming with space-time problems, 100,000 might still be slow because the matrices change form. Okay? And it seems like going beyond this point is much more of computational science than statistics. You know, this is all about how can we deal with these huge matrices on a kind of computational cluster environment, and this is getting very computational science. there is also this issue is that if we were able to provide a kind of high performance computing solution that requires that you have a computational cluster, you have to install everything, this is getting quite technical. And then the question is, will this solution ever be much used, you know? Most people just want to run it on their own laptop, and they're kind of getting annoyed if they have to go somewhere else, you know? And so I'm not quite convinced. And the other thing is that if we really should kind of treat huge space-time models, or if we should do that kind of more specifically, where we kind of can make sure we can make use of more of the structure, we can do things more specifically, instead of saying that, we just have a huge model and we have to deal with it. You know? So if we know more, we can take more advantage of certain structures. And the other thing is that maybe for when things get really large, we're thinking about 1 million and above. It might be that being kind of Markov is not that of an advantage anymore, if that is the right tool. The problem is that this kind of sparse matrix libraries, they don't scale so well on a kind of massive parallel environment. And if you go to kind of dense matrix algebra, they scale much better and also much better supported. Okay, so maybe it's better in that cases we have to kind of revert back and to use the kind of lower dimensional dense formulation in some form. I don't know, but anyway, as soon as you're kind of in the dense framework, you can kind of essentially do what you want. Okay, so there is no kind of restrictions. So these are kind of speculations. Yeah, thanks.
Questions? So instead of MPI, have you looked at something like TensorFlow for kind of the next generation INLA? Because a lot of the very large matrix stuff seems to be the sort of things that the deep learning people are also interested in.
Yeah.
And they have special chips now in order to make them go really, really fast.
No, I haven't looked into that. No. But TensorFlow uses compute this gradients, huh?
We can look into exactly what it does.
Yeah.
But yeah, I mean, if your problem is you need very large linear algebra problems solved, then that seems to be what it's built for.
Okay.
Yeah, Aaron? So for these really huge GMRF problems, would it be worth actually just going back to the conditional independence structure rather than computing the full matrix, actually computing the junction tree of the conditional independence graph and compute all of your calculations actually just by sending smaller matrices around the junction tree, and you could still actually calculate all of the things that you could calculate if you had the full graph?
I don't see how this kind of would be a kind of benefit, no. But it's always the kind of option to kind of split, instead of treating the whole model in one, to kind of divide it into blocks.
Yeah.
And then we're kind of back into the kind of sampling idea.
Mm-hmm.
Okay, where you can treat you can treat exactly the conditional distribution or almost for very huge blocks, and you kind of put this all together. Yeah, so that's another kind of path that could be worth doing. But then we're back to sampling again, and I hope I should not do that. Yeah, but this is especially if we have this very huge problem for space and time. If you know the structure, then it's much easier to do that, instead of writing kind of general code that will kind of do this kind of blocking without knowing where all the elements are coming from. If you have the physical problem in front of you, it's much easier to kind of construct reasonable blocks. But that's also a kind of valid strategy. So that's why maybe this should be treated more specifically. I know Finn Lindgren in Edinburgh have been working on in this direction. So it's for a huge problem, kind of divide it into blocks and then having some overlap and use this to build inference. Yeah. But that's another kind of general strategy. It's very hard to write general code for doing that, really. Yeah.
More questions? Okay, let's thank Havard.